Lesson: Understanding Sources of Bias in AI. Understanding sources of bias in AI is crucial for ensuring fairness and equity in automated decision-making systems. As artificial intelligence increasingly integrates into various aspects of society, identifying, addressing, and mitigating bias becomes essential not only for ethical reasons, but also for the credibility and reliability of AI systems. This lesson outlines actionable insights, practical tools, frameworks, and step-by-step applications to help professionals audit and improve fairness in AI systems. Bias in AI can originate from several sources, including bias training data, algorithmic bias, and biases introduced during model implementation and deployment. Training data, often reflecting historical and societal biases, can lead to models that perpetuate or even amplify these prejudices. For instance, facial recognition systems have been shown to have higher error rates for people of color, primarily due to training on datasets lacking diversity. This exemplifies how biased data can lead to inequitable outcomes, necessitating careful examination of data sources and collection methods. Addressing the issue of biased training data involves several actionable strategies. One approach is to implement data audits to assess the representativeness and fairness of the datasets used. Tools such as IBM's AI Fairness 360 offer comprehensive libraries to examine and mitigate bias in datasets and machine learning models. These tools provide metrics to evaluate bias and fairness, such as disparate impact and equalized odds, allowing auditors to identify imbalances and inequalities in data representation. Additionally, synthetic data generation can be employed to augment datasets, ensuring a more diverse representation without compromising privacy, which is particularly useful in sensitive domains like healthcare. Algorithmic bias can arise from the design of the AI models themselves. Certain algorithms may inadvertently favor majority groups if they are not carefully calibrated. To combat this, fairness-aware algorithms have been developed to ensure equitable treatment across different demographic groups. Techniques such as reweighting, resampling, and adversarial debiasing can be integrated into the model training process to minimize bias. For example, adversarial debiasing introduces a secondary model that attempts to predict sensitive attributes, while the primary model learns not to encode these biases, thereby promoting fairness. Another framework for addressing algorithmic bias is the use of fairness constraints during optimization. For example, fairness through awareness ensures that similar individuals are treated similarly, while fairness through unawareness attempts to ignore sensitive attributes altogether. However, the latter may not always be practical, as indirect discrimination can still occur. Therefore, fairness through awareness, which explicitly considers sensitive attributes to ensure equitable outcomes, is often more effective. Implementing these fairness constraints requires careful consideration of the societal context and ethical implications, as the balance between fairness and utility can vary depending on the application. Bias can also be introduced during model implementation and deployment. This often occurs due to a lack of diversity in the teams designing these systems or insufficient stakeholder engagement during the development process. To mitigate these issues, interdisciplinary teams comprising individuals from diverse backgrounds should be involved in the design and deployment of AI systems. Moreover, engaging with affected communities and stakeholders can provide valuable insights into potential biases and avenues for improvement. This participatory approach not only enhances transparency, but also builds trust in AI systems. Continuous monitoring and auditing are essential to maintain fairness in AI systems post-deployment. Bias can evolve over time as societal norms and data distributions change, necessitating ongoing assessment. Automated monitoring tools can track model performance across different demographics, alerting auditors to potential biases. For instance, Google's What If tool allows users to ask counterfactual questions and visualize model behavior across various scenarios, aiding in the identification of biases that may not be apparent during initial development. Case studies highlight the real-world implications of bias in AI and the effectiveness of various mitigation strategies. A notable example is the COMPAS algorithm used in the U.S. criminal justice system to predict recidivism. Research revealed that the algorithm disproportionately labeled Black defendants as high risk compared to white defendants, illustrating how bias in training data and model design can lead to unjust outcomes. In response, researchers have proposed fairness constraints and reevaluated the features used in the model to address these disparities, demonstrating the importance of continuous auditing and refinement. Statistics further underscore the prevalence and impact of bias in AI systems. A study by the National Institute of Standards and Technology found that many commercial facial recognition systems exhibit significant racial and gender biases, with error rates for Black women being up to 34% higher than those for white men. These findings highlight the urgent need for robust bias detection and mitigation strategies across various AI applications. In conclusion, understanding and addressing sources of bias in AI is a multifaceted challenge, requiring a combination of data audits, fairness-aware algorithms, diverse and inclusive teams, and continuous monitoring. Practical tools and frameworks, such as IBM's AI Fairness 360, fairness constraints, and participatory design approaches, provide valuable resources for auditors seeking to enhance the fairness and equity of AI systems. By implementing these strategies and learning from real-world case studies, professionals can effectively audit and mitigate bias, contributing to the ethical and fair deployment of AI technologies.